Okay, so we're going to begin our discussion of intermolecular forces and the structure of solids and liquids by talking about phase changes. So, harkening back to the introduction, when we say phase change, which is something that we got done talking about indirectly quite a bit in Chapter 8 and Chapter 9, when we're talking phase change, we mean transition from a solid to a liquid, or a liquid to a gas, gas to liquid, or liquid to solid. There are other phases of matter out there than kind of the big three that we usually talk about. But anytime you're talking about changing a process or a reaction that changes the state of matter of a chemical rather than the chemical identity, we call that a physical process or a phase change. So if we're taking and melting water ice to make liquid water, that's a phase change. If solid CO2, dry ice, sublimes, goes to gas phase CO2 directly at room temperature and 1 atmosphere pressure, that's a phase change. So anytime you're talking about going from solid to liquid, solid to gas, gas to liquid, gas to solid, that's a phase change. You're changing how the molecules or the particles in a sample are ordered. You're not changing the chemical identity of the chemical. So you're breaking intermolecular forces in a phase change. You're not breaking covalent bonds. Okay, so in a phase change, the physical state of matter changes, but the chemical composition of the compound doesn't. Another way of saying that is in a phase change, intermolecular forces, IMFs, are broken, but chemical bonds are not broken. We can still represent these processes with a balanced chemical equation. We just see by the fact that the chemical formula between the reactant and the product doesn't change that we are undergoing a physical process because the phase subscript or the phase label changes, whereas the chemical formula does not. Liquid water boiling to form gas phase water can be represented as H2O liquid goes to, in the presence of heat, that's what the delta is for, vapor phase water. We talked a little bit about the enthalpy of phase changes when we were in Chapter 8 talking about thermochemistry. When we're in Chapter 9 talking about thermochemistry, and I mentioned to you that there are enthalpies associated with just the phase change. Once you get water up to its boiling temperature, which would be 100 degrees Celsius, 212 Fahrenheit, around 1 atmosphere of pressure, once you've raised it up to its boiling point, you still have to input more energy to actually force the molecules into the gas phase. And that extra bit of energy that you have to put in to take water that's at 100 degrees and actually truly evaporate the sample and turn that liquid water into gas phase water is what's known as the enthalpy of vaporization. And for water, that is 40.7 kilojoules per mole. Where's that energy going? What's that energy doing? Well, at that point, that energy is overcoming, you can think of it from a molecular perspective, as essentially that energy is overcoming the last residuals of the attractive forces that are holding the bulk of those water molecules together in the liquid phase. And so from a molecular standpoint, the primary difference between water in the liquid phase and water in the vapor phase is that gas phase water, vapor phase water, the molecules are much more spread out. They're not close to one another. They're in constant motion. And so the enthalpy of vaporization is one measure of how, in a specific set of circumstances, you need to put in this amount of energy to actually sever the attractive forces that hold water molecules close together in the liquid phase and transition it into the gas phase. So what I really want to emphasize here is that when we're talking about intermolecular forces, we're talking about the attractive forces that do exist between two water molecules and attract the water molecules together. We are not talking about the covalent bonds that hold the atoms together inside the water molecule. Where do these types of intermolecular forces or intermolecular interactions come from? Well, the strength of the intermolecular forces are the primary determining factor in how large a boiling point or a melting point a solid or a liquid is going to have. The stronger the intermolecular interactions, the higher the temperature you have to get the sample to turn a solid into a liquid or to turn a liquid into a gas. There are intermolecular forces that act between all molecules, and they interact between atoms if you're talking about an elemental state of matter, an elemental chemical like a pure metal, silver or gold, where the atom is the molecule and the atoms are just attracted to one another. There are intermolecular interactions that hold the molecules, the particles together in all states and all forms of matter. However, depending on the chemical formula and the molecular geometry of the molecules in question, these intermolecular forces can be stronger or they can be weaker. So what we want to talk about in this segment is how we recognize the types of intermolecular interactions that molecules have, where these intermolecular attractions come from, and ultimately how we can decide what types of intermolecular forces a molecule has based on its molecular geometry and how strong the intermolecular forces are going to be. To get a handle on intermolecular forces, we have to first consider the way in which electrons are distributed in a molecule. So keep your eye on the moving parts here. And just as a final reminder, in this chapter, when we're talking about overcoming intermolecular forces, we're talking about overcoming the attractive forces that act between molecules. We're not talking about breaking covalent bonds between atoms inside a molecule. So we're talking about this, not this. We're talking about this, not this. Okay, to recognize the types of intermolecular forces that a molecule has, we need to know whether the molecule is polar or not. To understand whether a molecule is polar or not, we need to review the concept of electronegativity. You were introduced ideally to electronegativity and polarity sometime during Gen Chem 1. So hopefully this will be mostly a review, but it's going to be a very necessary review. We've got to review electronegativity, we've got to review how to get Lewis structures from chemical formulas, and we have to review molecular geometry ultimately to decide what types of intermolecular forces a molecule has. So what we're going to do today, mostly with our first day of lecture, is just review those three big concepts. And when we come back tomorrow, we're going to put those three things together and talk about how we can decide whether a molecule is polar or nonpolar, and what that means for the type of intermolecular forces that the molecule has. Okay, so ultimately when we talk about the polarity of a molecule, we're going to be talking about electronegativity differences between atoms and what that means for the distribution of electrons inside the molecule. Because as it turns out, the attractive forces that hold molecules together is still based on where the electrons are, but it's based on where the electrons tend to be in a molecule, not in a single bond. So a couple things to remember, that because of the quantum nature of electrons, electrons are kind of everywhere in a molecule simultaneously. But on average, they tend to be more likely in certain spots in the molecule than in other molecules. And if you look at a simple molecule like hydrochloric acid, HCl, you have a hydrogen atom and you have a chlorine atom. Chlorine has a higher electronegativity than hydrogen does. And so what that means is, on average, most of the electrons are on the chlorine side of the molecule, and very few of the electrons are on the hydrogen side of the molecule, on average, at any given time. What that's ultimately going to mean is that for a molecule like HCl, or any other polar molecule, while you never have real charges inside the molecule, you never have a positive charge and a negative charge, you do have one end of the molecule where the electrons tend to be more often. So you have kind of a partially negative end of the molecule, and you have kind of a partially positive end of the molecule. How those electrons tend to be distributed is based on that property you've met before, which is electronegativity, abbreviated with an italicized X. And electronegativity is the ability of an atom to attract electron density that is held in a covalent bond. So if you go back to Gen Chem 1, you were taught at some point to identify the electronegativity difference between an atom like chlorine and an atom like hydrogen. Chlorine is more electronegative, and therefore it gets to dominate the electron density that chlorine and hydrogen are sharing in this covalent bond. There's 2 shared electrons in this covalent bond. Chlorine is better at pulling electron density towards its nucleus, and what that means is in this covalent bond, the electron density tends to be on average closer to chlorine and less of it around hydrogen. In kind of a three-dimensional picture of the molecule, then, we represent that with what's known as an electron density map.